Now, capacitors can exist in a variety of configurations, and oftentimes you may have capacitors in parallel configuration or a series configuration. Thus, we need to construct expressions to determine an equivalent capacitance based upon their configuration. Say we have a current source I, where we have capacitors C1, C2, all the way up to Cn in a parallel configuration, and we want to determine our equivalent capacitance. To do such, we have to recall that elements in a parallel configuration have the same voltage potential existing across them. To analyze this system, we're going to apply KCL at the top node. We see that we have I coming from our current source entering our top node. We have I1, I2, all the way up to IN entering the top of our capacitors. If we express our currents in terms of our capacitance and voltage, I is equal to C1 dV dt plus C2 dV dt all the way up to Cn dV dt, where dV dt is the same value because our capacitors are existing in parallel configuration, and we see we have C1 plus C2 all the way up to Cn being the leading coefficient for dV dt. We can say that our parallel capacitance, or our equivalent capacitance, is equal to the sum from I is equal to 1 to n of C sub I. This is the inverse of resistors in a parallel configuration. Now, capacitors can also exist in a series configuration. Imagine we have C1, C2, all the way up to Cn in a series configuration, and we have a voltage source applying a voltage potential to our circuit. To determine an expression for equivalent capacitance, we have to recognize that elements in a series configuration carry the same current, and thus we can apply KVL around our loop. If we apply KVL around our loop, we have V, our voltage source, is equal to V1 plus V2 all the way up to Vn, where V1 is our voltage drop across capacitor C1, V2 is our voltage drop across capacitor C2, and V sub n is our voltage drop across capacitor C sub n. In terms of capacitance and currents, our voltage is equal to 1 per C1, I of tau d tau, plus 1 per C2, I of tau d tau, plus 1 per Cn, I of tau d tau. Each capacitor is carrying the same current throughout. We'd recognize that we'd have 1 per C1 plus 1 per C2 plus 1 per Cn being the leading coefficient for integral of I of tau d tau. Thus, our equivalent capacitance for capacitors in a series configuration is equal to 1 per Ceq is equal to the sum from I is equal to 1 to n of 1 per C of I, the opposite of resistors in series configuration.